You go to log in, you type your password, hit enter, and the site checks it. Right password, you're in. Wrong one, try again. Simple. Except, here's something genuinely strange. A well-built website never stored your password. It is not sitting in a database somewhere with your name next to it. The company running that site couldn't tell you what your password is even if you begged them. They honestly don't know it. And yet, every single time, they can tell you whether you typed it correctly. So, how does a server check a secret it doesn't have? Here's the trick. When you first set your password, the server doesn't save it. It runs it through a special kind of function called a hash function. That function takes any input and turns it into a scrambled string of characters called a hash. Type hunter2 and out comes this fixed jumble that looks nothing like what you typed. And that, the hash, is the only thing the server keeps. The magic is that the hash function runs only one way. Forward is instant. Password in, hash out. But backward, taking the hash and working out the password that made it, is, for all practical purposes, impossible. There is no unscramble button. So even if someone steals what's stored, they don't have your password. They have a fingerprint of it. So how does logging in work if your password was thrown away? It just does the same thing again. You type your password, the server hashes what you typed right there on the spot and compares that fresh hash to the one it saved when you signed up. If the two match, you must have typed the same password, so it lets you in. If they don't, you didn't. This works because a hash function is perfectly consistent. The same input always produces the exact same hash every single time. So the server never actually compares passwords, it compares fingerprints. It can recognize your password without ever knowing what it is. Now, two things make this fingerprint trustworthy. First, it's always the same size. Whether you hash a single letter or an entire novel, this kind of hash, the common one is called SHA-256, always spits out 256 bits, 64 characters, no more, no less. And second, watch what happens when I change the password by just one character. Hunter2 becomes Hunter3. The result isn't even close. It isn't similar. More than half of it is completely different. That's the whole point. A hash gives you exactly one piece of information. Match or no match. It never tells you you're getting warmer. It never hints how close a wrong guess came, which is exactly what you want standing guard over a secret. But that perfect consistency has a dark side. If the same password always makes the same hash, then everyone who chose the same password has the exact same fingerprint sitting in the database. And attackers know which passwords people usually pick, so here's what they do. They take a huge list of common passwords. Password 123456, Hunter2, and they hash every one of them, just once, ahead of time. They build a giant lookup table from hash back to password. Then, they steal a site's database and simply match rows. Any user whose hash is already in the table is cracked instantly. They never reversed anything. They just recognized it. The fix? Well, it's beautifully simple. Before hashing, the server mixes in a little extra, a random value called a salt, different for every single user. Your password and your salt get hashed together. Now, two people with the exact same password end up with completely different hashes because their salts don't match. And that giant pre-computed table the attacker built, useless. They'd have to build a brand new table from scratch for every single user's unique salt, which throws away the entire advantage of computing it ahead of time. The salt isn't even a secret. It's stored right next to the hash. It only has to be one thing, different for everyone. Now there is one last problem, and it's the one people never hear about. A hash like SHA-256 was built to be fast, and for passwords, fast is exactly wrong. Salt stops the pre-computed table, but an attacker holding your salt hash can still just guess. Hash password with your salt and check. Hash 123456 and check. And a single modern graphics card can try billions of guesses a second. Against a weak password, a fast hash loses. So, well-built systems don't use plain SHA-256 for passwords at all. They use hashes deliberately engineered to be slow, with names like Argon2, bcrypt, and scrypt, tuned so that no one hash takes a noticeable slice of a second and deliberately hogs memory. You'll never feel it on the one check when you log in, but an attacker trying to grind through billions of guesses now needs years and a fortune in hardware instead of an afternoon. Okay, so now let's put it all together. The server never stored your password. It stored a fingerprint, run through a one-way function, mixed with a random salt so no two are alike, using an algorithm deliberately too slow to brute force. Every time you log in, it builds that fingerprint again and checks it matches. It recognizes you without ever knowing your secret. And that's why, when you hear that some company leaked its password database, the good ones didn't leak your password at all. They leaked a pile of salted, slow fingerprints that are close to worthless without months of work for each single account. Your password was never sitting there to be stolen. The computer checking it never knew it in the first place. Everything you just figured out rests on something deeper, and that's the next video, so start there. Would you rather understand your computer than just use it? Then subscribe, and I'll see you next time, further down the stack.